this actually means. So examples in R2 where everything is always easy to see. So for example, in R2 we take S equal to 3 vectors, 1, 0, 1, 1, and 1, minus 1. So these 3 vectors, they span R2. Every vector can be written with the help of these 3 vectors. But we know R2 has only dimension 2. So these 3 vectors must be linearly dependent. And obviously, we can see this. If we add these 2 and divide by 2, we get this. Or if we take this times -1 plus 2 times this, or no, plus -1 this, we get this. So these are linearly dependent. So what we can do is now, we can go from S in different ways. For example, I can say I delete this vector. And it turns out these 2 vectors still span R2, sorry. So this is a basis because they span, you can check the determinant is non-zero. So this is a basis. So from these 3 vectors, we reduced it by 1 vector to get this as a basis. Or you can actually take out this guy. We can also go to 1, 0, 1, minus 1. Again, if you calculate the determinant is -1, non-zero, that's also spans R2. So as here, it's a basis, and this is a basis. Or you can actually also delete, for example, this guy. And this is a base, as again, spans R2, and it's a basis. So what it means, if you have too many vectors which span your vector space, too many means more than the dimension, you can delete some vectors, and the remaining vectors are still a basis. But be careful, you cannot always reduce every vector. It depends. So the remaining vectors must still be a basis. So the vector you delete has to be a vector which can be written with the help of the other ones. So that's important. Can I write this with the help of this? Yes, so I can delete it. Can I write this with the help of this, guys? Yes, so I can delete it. Can I write this with the help of these? Yes, so I can also delete this. So you can only delete a vector if it's a combination of the other vectors. And for this kind of small example, in 2 dimensions, you can just do it in your head. You say, this guy, can I make it with the help of the other one? If you have a larger problem with 5 vectors, also with vectors with 5 components, that might be really complicated to figure out which one is a combination of the others. Each time you have to solve a linear equation system. But for the small examples, like here, dimension 2, you can see, oh, that's easy. So this is what we call a reduction. So from a vector set of vectors that span, we can reduce it to a basis. And so that was one direction. The other direction is when you start only with 1 vector, and again, I just make up 1 vector. This vector for sure is linear independent. It's only 1 vector and it's not the 0 vector. Now, 1 vector cannot make all of R2. So we can add another vector to make it a basis of R2. And again, we can go from S and add arbitrary other vectors to make the whole of R2. When I say arbitrary, it means more, there are infinitely many choices, but you cannot add every vector. Just you need to add a linear independent vector, something which is not in the span of 1, 0. So it's not along the x-axis. So we can make, for example, this vector and this vector. So I add this vector, and for sure, these are 2 vectors. They are linear independent. Dimension is 2, so automatically that's a basis. But I can also add this vector. Again, these are linear independent. Determinant is 1. So that's a basis, always of R2. Or you can actually, there are many, many other choices, as I said. For example, 1, 0, and for example, -1, 1. Again, determinant is 1, 1 minus 0. So that's a basis. So if you start with a set which is too small but linear independent, you can add other vectors to make it a basis. So this is reduction, this is extension. And again, as I said, in the two-dimensional case, that's very easy to see. But in higher dimensional cases, it's more difficult in the sense that each time you have to figure out, this guy, is it really linear dependent of the previous vectors? Keep in mind, for example, in 5 dimensions, I can give you 4 vectors and ask, what other vectors can I add to make it a basis? And then right away you're in trouble. You have to look always, is this 5 vector independent of the other vectors? Means not in the span. Okay. Yeah, and it's clear I can only add vectors that are not in the span of this. So for example, I cannot add 2, 0, no? Because if I add 2, 0, I add a vector which is already in the span and it's useless. No? So it's also not linear independent, so it cannot be a basis. And again, with 1 vector, that's easy. With 2 vectors, to show that something is not in the span already means you might have to do a Gauss algorithm. Okay, so this means sets which are too large, you can reduce to bases. Sets which are too small and linear independent, you can extend to bases. Okay, but coming back to what I said before, so the main point in this section is that if you have a vector space with a certain number of basis vectors, let's say 5, it means every basis has 5 elements. And this 5 is what we call the dimension of a vector space. Most of the calculations, like I showed you, for example, before when we solve a linear equation system, most of the calculations connected to dimension are, again, Gauss algorithm or Gauss-Jordan algorithm. But number of independent vectors in your basis, that's what we call now the dimension. Okay, as I said before, chapter 4 is really the center of this class where we learn about vector spaces. And there's one more section, 4.6, that will be tomorrow at the beginning, pretty short, where we talk about, again, if you have 2 bases, how can we actually change coordinates between bases? So that's something you might actually, yeah, like my plane example, that's, for example, something where you can use this. After this, so tomorrow actually, in the second part tomorrow, or maybe already after, because the section is very short, 4.6, we go back to our main problem, why we actually started the whole thing. If we look at linear equation system and matrices, and they're maybe not square, or they can also be square, how do we use now all this, what we learned for vector spaces, to study matrices and linear equation system? So that starts in 4.7 and 4.8. And after 4.8, that's it for linear equation systems. Then we know everything what can happen. Most of the calculations are always Gauss algorithm. But we know for sure that we understand the structure of what can happen to the solution to a linear equation system. So by Wednesday, we will have finished this. And then after this, we go more back to the geometry of matrix transformations. And that will be also the last section in chapter 4. And that's also the topic of chapter 5. Okay, like I said, this is always a lot to digest because it's always definitions and what do they actually mean. Okay, any more questions about what we did today? Otherwise, I will stop sharing the screen and then I see you either tomorrow or later at 3 o'clock for the office hours.
Okay, thank you, Professor.
Okay, and also I will try to remember, I will post the solution to the exam also later. I need to scan it. So take a look at the website where it says something. Also last week it said somewhere, oh, we have our exam. And then I will make a link there for the exam solution. No?
Professor?
Yes?
I'm just curious, like how we did as a class, if you have that information.
I also, if you like, it's a kind of a bimodal. Also the most, actually, the biggest number of students have actually A's. but we have also a few students who didn't do so well. Also, if you like, I can post this.
Okay.
Yeah.
If you don't
usually
mind.
I make always a table on the board, but here it's harder to do this. So yeah.
Okay. Thank you.
Any other things?
Yeah, Professor?
Yeah.
Is the exam next week going to cover everything from like the whole?
I will give you a list of sections for the exam. But for sure it will cover chapter 4 and 5. But now the point is, when you look at chapter 4, no? When you think about so I will say something like, oh, it will only cover chapter 4, 5, and maybe 6 if I can touch it, no?
Mm-hmm.
But if you look at all the calculations, that's not a calculation now, but if you think what I did before the break or before this paper, the Gauss algorithm reduced row echelon form is always there, no? So yeah. It doesn't really help you when I say it's chapter 4, because every calculation in chapter 4 we do is either a determinant or a reduced row echelon form, no?
Mm-hmm.
So for this reason, yes, for sure, I will tell you it will be only chapter 4 and 5. But in order to do these questions, you need chapter 1 and chapter 2, no?
Yeah, but like...
For example, the cross product will go away. Because the cross product is not in general. The cross product is very helpful if you do three-dimensional geometry, no? Like, you remember, you can calculate the area of a parallelogram, area of a parallelepiped. You can actually calculate the surface normal. That's all important if you do computer graphics, no? So cross product is really important for computer graphics or three-dimensional geometry. But here, it doesn't play a role because we're talking about Rn, and we actually don't even know what a cross product in R4 is, no?
Mm-hmm.
So cross product, you can say, oh, you're right, that will go away, no? So cross product will not be there in the last exam, no?
Okay.
But the point, my point is, even if I tell you only chapter 4 and 5, you need large parts of chapter 2 and chapter 1.
Yeah, but you said that you...
Yeah, sorry, yeah, that's how it is.
You said you mostly make your exams based on like the homework though, right?
Right. And if you look at the exam from Thursday, then I mean, I hope at least every question you had there was a question with different numbers somewhere on your homework, no?
Mm-hmm.
Yeah.
Okay, thank you.
Yeah.
Professor, since we're ahead of schedule on the syllabus, will our exam still be on that Thursday, or will it be pushed forward?
No, it will be on the Thursday. Actually, to be honest, I don't think I'm too much ahead of schedule, because actually I'm more concerned that I cannot cover chapter 6 actually in the moment. Yeah, I always try to push a little bit forward when I can, but it turns out, because the reason is I know, especially chapter 5, I might need more time than I have in the syllabus for it. No.
Okay.
Yeah. Also, I will not, whatever happens, I will not change the exam date, because then it always happens that, oh, someone cannot come or something, no? Any other questions? Okay, so then I finished the screen sharing and post the videos later. And at around 3, I send out again a link for office hours today. Okay, thank you.